Hello everyone, I'm Degenerative and I'm a senior postdoc in CIMIC here at UCL. And today I'm going to talk about some deep learning framework that I've worked recently in the last few years. And the applications are on health informatics and medical intervention. And specifically in the last part of the seminar, I will introduce our recent framework called Degenerative Adversarial NeuroImage net. To generate synthetic images that emulate the progression of disease. So I will give initially an introduction on deep learning. I'm pretty sure you know a lot about this. And I will cover three different projects that I was involved in recently. One is in the field of smart sensing. The second is super resolution for image modality that is called endomicroscopy. And the last project is called for tumor segmentation using adversarial imaging. And later we introduce this framework called Degenerative, as I mentioned before. So a few years ago, we realized that deep learning was an emerging tool to be used for solve medical application and application in health informatics. What is the reason why deep learning has become popular? There are many reasons. One main reason is definitely the fact that medical center and hospital, they start to organize and collect properly data. So these are a large amount of data and contribute to the success of deep learning. The second reason is because parallelization in the last few years have become very powerful a very powerful device, such as the fact that GPU have become very strong. So since 2010, the number of papers published in health informatics have risen exponentially in all the area of health informatics. And this trend is continuing still today. Deep learning is actually not only one framework, but is a family of framework. And it depends on the type of data that you have or the application that you want to solve. You may be interested in one of these framework or a combination of these framework. For example, if you have multidimensional data, such as an image or an MRI, you may use convolutional neural network. If you want to solve unsupervised application, for example, for generating synthetic images, you may use a generative adversarial network. If you are interested in model sequential data, you may use a recurrent neural network. If you want to compress the data in a small representation, you may use deep autoencoder. And if you want to learn the relation between statistical variables, you may use a deep belief network. So the first field that where we used deep learning a few years ago was the smart sensing. What is smart sensing? It's the field where we develop devices that can be wearable or implantable to monitor some biological physiological parameters. In my case, the idea was to monitor the calorie that each person burn or intake during the day. So we developed this ER sensor that the people they have to wear during the day, and the ER sensor is provided with some accelerometer that provide sequential data that can be analyzed using this neural network. At the same time, the device was provided with a microphone that recognizes when the person chewing, and it starts to recover the food that is intaking. And we were able to classify the food that eventually estimated the calorie that intake. And the last sub-project in this field was to create this device that is in the first image to help people that suffer of COPD to identify area in the city that they are highly polluted and eventually avoid this area in the next day. The second field where, again, we used deep learning was for performing super resolution in endomicroscopy images. So this endomicroscopy images is a image device that work at very slow scale, and due to the physical constraint how this device works, the image have a really low quality. Here the images they are called histologic-like images because they are similar to the histologic result, and therefore they can help doctor and surgeon to provide in real time diagnosis for possible cancer. So, however, as I mentioned before, since this image quality has a low quality, these images, they have noise, they have low contrast and artifact. And the idea is to create a framework that try to solve all these issues at the same time. In our specific case, we developed an example-based super resolution where we train a network with unpaired images. More specifically, we have a low-res images coming from the initial domain, and we train a framework that is it has a cycle consistency based on the physical acquisition property to create a high-resolution images. Finally, the third project before the last one is this brain tumor delineation. So the idea here is to use light to characterize a tissue. Researchers have discovered that when the light hits the tissue, the light is divided in different components. These components are the absorption, reflection, and scattering. According how these components are divided, we can discriminate the tissue. More specifically, researchers show also that the absorption spectra characterize the concentration of oxygen and saturation of hemoglobin, and this is correlated with the hypermetabolism and the angiogenesis. See, so all this information can be described using hyperspectral imaging. So this hyperspectral imaging is a device, it's a camera device that acquires a channel at different frequencies in the visible and not visible range. And a signature in this frequency domain allows the discrimination of the different tissue. Here the problem is that we have a large amount of data that we have to process, and the idea was to provide a framework, a deep learning framework that compress all this data and eventually can visualize better the discrimination between the different tissues. This is the setup of our device that was bring inside the theater, and during the resection of the brain tumor, we were able to show in real time the segmentation map. So these are the results from the compression of the image, and as you can see in the images are shown a lot of details such as vessels or the area of the tumor. After this, we can perform semantic segmentation to create the classification map. Finally, recent success of deep learning have shown that there is the possibility to train a framework that can learn cross-sectional data to model longitudinal study. So in this case, the idea is given the images of a face, we are able to predict the future look of the person or eventually estimate the previous look of the person. So I try to apply the approach on myself to verify that it was working. And as you can see, the algorithm is able to create wrinkles or eventually remove wrinkles, but not the beard, because I don't think when I was 11 I had the beard. So our idea was to use a similar framework to do something more interesting, and more specifically, at the same way that the framework is able to generate wrinkles in the face, we thought that we could generate atrophy in the brain, and eventually model disease progression and aging of the brain. So again, the idea is to, given an MRI, we can predict and simulate the progression along the aging, and at the same time we can regress this MRI. What are the applications for this approach? One application is definitely predict patient outcome and validate a progression model. Another application can be the estimation of the most likely trajectory that the disease took to arrive at the point that we are right now. So this is the framework that we propose. Basically, the core of the framework is based on a conditionally powered encoder, and there are different other components such as discriminators and framework based on support vector regressor. They try to model a different component for allow this simulation. So let's go one by one. The first component is the component that tries to model the deformation that preserve individuality. That means we want that along the simulation the images maintain the morphological structure of the brain of the individual. The second component, it models the fact that the images that we generate, they should contain a realistic brain structure. The third component is a condition component, and basically it allows us to condition the framework with different variables such as diagnosis or other external information, and this basically allow the system to characterize the progression differently according to these variables. The fourth component is the temporal smoothing. That means along the simulation, there are no jump of consecutive images that we create. And the last component, that is the most important component, model the biological constraint. So what are these biological constraints? They are based on so they try to model atrophy and volume shrinking in the brain. And these are the one colored in orange in the slide. Mainly, we developed two functions for this biological constraint. The first function is operate at voxel level, and the second function operate at region level. And the idea is to train supervector regressor region-based that try to predict the rate of intensity progression that, as you can see from the graph, it should be monotonically decreasing. And this simulate the aging or the disease progression in the brain. And each region progress differently, and this supervector regressor help the deep learning framework to model the disease accurately. To validate our framework, we use ADNI. Specifically, we use T1 weighted MRI. And we use around 90,000 MRI images from 876 participants, and for the test, around 1,000 images from 179 images. And each participant has an average 4.7 MRI spanning 3 years. So for the validation, we use quantitative and qualitative analysis, and we analyze the different component of this framework to verify which one provide the best contribution. And we assign a letter to each of these components, and we also combine this component differently. The performance are measured using this structural similarity index, and the idea is to measure the similarity between the simulated images and the real ground truth that we have in ADMI. And as you can see from the table, the pipeline that consider all the 3 components enabled is the one that provide the highest contribution. The baseline that in this case is identified with the number 8 is the approach that was using the phase progression. And from the table we can also see that the progression and condition are the components that provide moderated contribution, whereas the transfer learning is the one that provide the highest contribution. Here are some more visual results. So in the first line, we have the input image X and the real ground truth Y. Second line, it shows some of the synthetic images generated by different configuration of the framework or from the baseline 8. And in the last line, we can see the error maps. And the error maps, it is so if there are no error, it will be completely white. So we prefer to have a completely white error map. And as you can see, the configuration that use again all the 3 component active, that is PCT, as the best error map. I don't know what's happening there. So the number are all mixed. I can describe. So here we perform a qualitative analysis where we ask 25 medical image experts that are neurology or image or computer scientists to evaluate 3 different synthetic images, and they have to pick between these 3 synthetic images the one that is close to the real ground truth. We repeat this 36 times per each participant. So in average, they have to evaluate 36 sets of synthetic images. And again, in this qualitative analysis, we show that the participant selected 72% of the time the configuration that use all the 3 components, while I think it is 5% of the time where the participant was not happy at all with any of the 3 synthetic images, and I think it was around 2.7% of the time that they pick the baseline. So again, the pipeline that we propose is a considerable improvement with respect to the baseline. Here one more video that shows the result that we obtained. So the first image is the input image. The second image is the generated image, and the last is the difference between the generated and the input, so that we can see which area the progression is modeled. And the map, it is green if it is before the baseline, and it will be red if it is after the baseline. So hopefully it works. So the video is shown first in slow motion, and you can see the ventricle gradually increase, sorry, and the cortical become so the volume shrinking from the external part. And again, this is another example. First in slow motion, and then okay, I think it's enough. And here a few more examples. So each line is the simulation of a different patient. The red block is the input image. So the one outside the block are the simulated images. And again, you can see the ventricle expanding, and you barely can see the volume shrinking of the brain. So in conclusion, we have developed a new deep learning framework that is able to emulate the effect of neurodegeneration in structural MRI. I've also introduced a few more approaches in different fields where we have used deep learning recently. In the future work for this last project, we are planning to extend the framework in 3D because currently it works only on one slice of the MRI. And we are also thinking to include more conditional variable and eventually use a different image modality for a different other disease in other organs. And with this, I conclude my